Today we sat down with Ian Fairweather of Fairweather IT. His organization was kind enough to praise Einstein on social media for our USD-1 radar altimeter after a much-needed successful deployment over an environment that cannot be accessed by human beings. We discussed the challenges Ian has overcome through the use of his UAV in marine technologies, along with the benefits of leveraging Einstein's radar altimeters over areas that are not only dangerous to humans, but also his machines. Hello, and thank you very much for joining. This is Einstein, Jason Etter here, Director of Marketing, and I'm really excited to talk with Ian Fairweather, President of Fairweather IT, or as his friends and his customers called, FIT. That's the other way to go, and we'll probably refer to Fairweather IT as FIT throughout the rest of the conversation because it just sounds cool and it's a lot easier to say, rolls right off the tongue. So Ian, thank you so much for joining us today.
Oh, thank you for having me. It's a pleasure.
So we're going to talk a lot about, how Einstein and FIT work together. But before we do any of that, so anyone that's not familiar with what FIT is, could you just give us a bit of an overview or even a little history behind it?
Yeah, certainly. It's we call ourselves an applied science and technology consulting firm. I founded FIT about 8 years ago to provide technical support to a mining remediation client here in Montana. And what they like about us is our flexibility. Due to the smaller size of our company, we're very flexible in being able to find solutions to a multitude of problems that come up. And we try and solve those using technology. My educational background is in remote sensing and geophysics. So that's how I kind of got into the whole UAS systems. And it was to collect high resolution imagery, specifically calibrated multispectral imagery for vegetation health analysis on mining remediation sites. Using the knowledge we gained from that, we leveraged that and moved into doing some photogrammetry, mapping missions, creating 3D data products. And then with some additional, problems and safety considerations that we had with the client, we've then leveraged that information to use UAS to collect physical environmental samples and other geophysical data. So, and the main purpose of this is to collect that data in a safe manner that is repeatable.
Yeah, that's real. I mean, I was looking at your website. Now, I know before we started this, I was even just talking about how some of the aerial footage that you've taken. I mean, the environments you're in. I mean, I don't think many people have the pleasure of experiencing such really interesting, the landscape that you're around and just the different scenarios that you encounter.
Yeah, true. We work at the largest Superfund complex in the United States. So it extends all the way from Butte, Montana, through the Clark Fork River, including Anaconda, Montana, down the entire Clark Fork River system to Milltown. So individually, the Superfund sites aren't the biggest, but it's a conglomeration of multiple Superfund sites that are a result of centuries of mining in Butte, Montana. So we work in that environment. So it has everything. It's high altitude. There are flat plains, there are mountains, there are treat areas, there's an active mine, there's a mine pit, just a larger variety of landscapes, terrains, and with that, a lot of different data that we can collect, such as the calibrated multispectral, the thermal, our physical water samples, water quality data, and so forth.
Interesting. And it seems like if I was reading through correctly and learning more about you guys, that you do a lot of studies that involve both aerial systems such as UAVs, drones, and even marine craft. Would you, just for anyone that's still trying to play catch up to understand exactly what you guys do, like what exactly are you examining during these deployments?
Well, yeah, so we developed the technology to process and collect environmental data. Specifically, we want to do it safely, we want to do it cost effectively, we want it to be repeatable, and we want the data to be high quality. One of our kind of flagship things that we've been working on, and what we'll discuss later, where we've integrated the Einstein radar altimeter, is our water sampling platform. So some of these tasks, you're just not able to collect that data with a person. In the past, we work at the Berkeley Pit in Butte, Montana. It's a large water-filled former mining pit. It has a diameter of about a mile. It's extremely deep, about 815 feet deep. Previously, to collect water out of that, they would go out in a boat and collect physical samples. Due to the hazardous temperature, thermal characteristics of the water, the chemical characteristics of the water, it's very acidic, has lots of dissolved minerals, and the unstable slopes, manned collection of water is not allowed. But we still need to know what the water quality, the chemistry data is in that pit. So we were asked to develop a safe method to remotely collect physical water samples and do deep, what we call water column profiles using a UAV. The result of that is what we call the WASP, or Water Sampling Platform, which is our patent pending technology to go out and safely collect those water samples. What makes it different than other methods, anyone thinks, oh, I can go collect a water sample, I'll tie a rope to the bottom of my UAV, I'll fly out, dip it in the water, get my water sample. Well, some of the depths that we're having to go to, it's not really feasible. And to the safety aspect, if you want to get a sample 200 feet deep, you'd have to tie a 200-foot rope to the bottom of your UAV, fly out there. When you get your water sample, you have say a 2-kilogram load suspended 200 feet beneath your UAV, which causes a very dangerous pendulum effect, which can result in the loss of aircraft. Where we're operating as well is right over a commercial flight line into the town of Butte, Montana. So our maximum ceiling altitude is 200 feet. So using that method, the deepest you could sample is 200 feet flat. Using our technology, we've integrated a winch and a remote controlled motor into our WASP, which allows you to suck up the payload to the bottom of the UAV so you get better flight characteristics, and we can sample extremely deep. To date, our current depth record is 813 feet below the water surface, which to our knowledge, we don't know anyone who has sampled that deep. We have 2 versions of it. We have one that works with a DJI M600 Pro. It's got about a 2-kilogram payload, and we have a heavy lifter, which is sitting right behind me here, and we can zoom into that a little bit later, which has a 4-kilogram payload capacity. So yeah, we use these UAVs and other marine crafts in the Berkeley Pit and other areas for this mining remediation. So some of the data we collect we do physical water samples to send it off for chemical analysis. We do water column profiles, and we're working on a sediment and sludge sampler where we could go out into the pit, deploy it down, and actually get a physical sludge sample from the bottom of the water. We also use the calibrated multispectral thermal imagery collection. A lot of what we do with the marine craft is for waterfowl hazing and interdiction. So in this pit of water, high in the Rocky Mountains, due to the depth and the chemical nature of the water, it rarely freezes over. So during waterfowl migrations, they go fly to the south in the winter and then back north in the springtime. It is often the only ice-free body of water in the area. So unfortunately, they think that, during times of very cold temperatures, the water actually keeps them warmer than the surrounding air. We do not like them to land on the pit, one, because it's hazardous chemically, and can be hazardous to their health if they stay too long. So we use marine craft that we've developed for hazing them. So if the birds are landed on the pit, we can get them off, and for preventing them from landing on the pit. So we don't even need to scare them off.
That's fantastic. That you just answered a slew of questions that I was gonna start going through. Like that. That's great. I was so curious about the difference between when you would use the marine device versus the UAV, and you just perfectly articulated that. That was really interesting. And I think it's such an interesting case. There are multiple bodies of water or just environmental areas that just human beings can't be in front of, and you still need to measure it, still need to understand what's going on. And you guys really have seemed to crack open a very interesting nut in terms of how to accomplish this, which is really quite amazing. Very cool stuff. So if it's okay, I'd love to get kind of into how we started knowing each other a little bit further. Something I'll make sure that is in the video is, you commented on LinkedIn saying, hey, this thing, we were able to do something very successfully. You were having some trouble before, a little concerned about the safety of your aircraft when you were doing some measurements. I'd love to understand a little bit more about what led you to Einstein and what issues you were having beforehand.
Oh, perfect. Yeah. So, I mean, some of the biggest hurdles we have with operating in this mining pit environment are operating at distance. We keep the UAV within our visual line of sight. We have some super bright lights on there that aid in detecting it. So when it's far away, but when the UAV is a kilometer away, there's no way you're being able to visually look at the mechanics of the WASP plate to make sure it's operating correctly, to make sure you're in the water, what depths you're at, and so forth. So one of the biggest hurdles that we deal with is operating at these distances. And from that, we're having to use telemetry data from our onboard sensors, which we have a number of, and the onboard cameras, so that the pilot in command, that's myself, and the equipment operator, the FIT employee that is operating the WASP plate, so we can see what we're doing. Another challenge is that we're actually operating the aerial UAV below us. So most people think when you're flying a UAV around, it flies up in the air and it's above you. Well, our zone of safety is about 60 meters above the surface of the water at a safe area. So when we're flying and collecting these water samples, we are actually flying the UAV below us, up to 50 meters below us, just in altitude range. So that's another challenge that you have to deal with. You have to, the UAVs are designed for flying above you. Flying below you, you have to deal with your antennas, flip your antennas around, and other fail safes. So if there is a loss of communication, the UAV doesn't try and come immediately back to you, that it rises up to a safe altitude so it doesn't crash into the wall when it's flying back. So those are kind of like the biggest challenges that we have to deal with. Another challenge is actually just dealing with the water beneath us. So we fly out, we want to be a distance of about 5 to 8 meters above the water before we deploy our sampling equipment. If you're too high, it's just too much space that you're dropping the payload through the air. If you're too low, you can actually get a spray from the prop wash coming back up and hitting your instruments, which you don't want with the high acidity heavy metals. So in the past, what we would do is we would just use the onboard GPS and barometer for altitude. This was flying, by the seat of our pants. We'd fly out there, we'd point our camera down on the water, and we'd lower it slowly till we could see the prop wash on the water itself. And from that, we would estimate our negative altitude. So say if the water is 60 meters below us, we'd go down to minus 52 meters, and that is what we'd use for our kind of baseline for our altitude. Now, as we all know, those barometers can be not the most accurate, if there are changes in temperature or whatnot, and we don't want to obviously crash the UAV into the ground. So one of our major challenges was trying to find a rangefinder that would actively detect how far above the water we are. Looking through user forums and researching with, these autopilots, many people use a laser or LiDAR rangefinder. We got one of those, we integrated it into our craft, and when we were doing our testing, which was over land, it worked fantastically. The values that we got from that laser altimeter matched the barometer and the GPS. We thought, oh, this is fantastic. We take it, go to the pit, do our one mission, we fly out there, and great over land. Once we hit the water, the numbers went all over the place. They went from 100 down to 000 and everywhere in between. Sometimes when we got lower to the water and we created enough rippling with our prop effect, we would get some values, but they're not steady and consistent. So we needed to find a different method for accurately measuring that range between us and the water surface. We looked at other LiDAR rangefinders, potentially using different wavelengths of light, different powers. We looked at sonar. Fortunately, sonar's got a very short range, and then onto radar data. And what we had found, in research is that the radar does operate well over ice and snow and over water. So we did some searches online, found a couple different vendors. We found Einstein. Luckily, you guys are located in the United States because our client prefers that we use U.S. vendors. And also that in the PICSOC, we use a PICSOC cube for our flight controller, that we can integrate it into our flight control system so we can get that telemetry data back in our mission planner apps and on our controller, so we can actually see while we're flying how high we are above the water. So for those reasons, we purchased a US D1 radar altimeter, integrated onto our craft, and we've been using it ever since, and it produces great stable range results to the water surface. Whether the water is still as glass, which happens sometimes, or there are waves due to the prop wash or to wind in the area, we get a stable range distance to the surface of the water. And what I guess I forgot to mention earlier, they are doing some water treatment in the pit. So it's not like the pit is a static level of water. It can raise and lower a bit. So each time we would go out, we would have to measure that distance that we could safely operate. Now we can just fly out and lower it down. We read the telemetry information back from the Einstein US D1 sensor, and we know how high we are above the water.
That's great. That's excellent. I believe it is behind you, right? I'd love to
Yes.
get a better understanding of how you put it together and how it fits, and if it didn't make any, it wasn't too problematic getting it all set up for you.
No, well, luckily it has a serial connection. So we were using the serial connection, not the COM port. As you can see here, we printed out some just custom little brackets to go around the arm, and a custom bracket to stick it out on the front arm. So on our UAS system here, this is a Watts Innovations MFD 5000. We taped up with reflective tape, the front arms being red. We also have a red, super bright 3 nautical mile visual light on the front. The same with the back with the green. But we put this going out on the front here, and with the cable from Einstein, we just clip that off and put a standard PICSOC serial cable connection on there to go into one of the onboard serial ports. And the parameters are online. They're easy to find in the ArduPilot wiki. We entered in those, and when we did the testing, once again, the values that we got from the rangefinder matched up with the GPS and the barometer altitudes. And this was above, ground level, not in the water, but it works great in the water as well.
That's excellent. That's great news. And I love the way that you put it about how it just easily integrated with what you guys were using already. I know that's something that we really try to be more of, like that open software solution or open technology stack offering, so that you're not having to then add another technology stack to your already functioning system. But rather than that, we can just sort of play with what you guys are working with to make your lives a little bit easier.
Yeah, absolutely. We don't need a companion computer, Raspberry Pi or anything. It plugs into the telemetry port on the PICSOC. The PICSOC provides the power, provides the data, as long as you have your parameters set up correctly, you can all find that online. And then you turn it on, you just make sure that those values are being shown in your flight app and on your controller, and just plain works. So
that's great. That's fantastic. No, that's really cool. So let's move, going back to Fit itself. I'd love to know a little bit more about what type of businesses do you work with? So if someone's watching this, they're like, wow, I would love to work with Fit. Like, who would that person be?
Well, we started off working with a large, international oil and gas super major who is responsible for the remediation in Butte and in Montana. And from that, we've stepped out. We've, worked with some national and international mining companies, for this water sampling, state and federal agencies. We've been in talks with the USGS Volcano Hazards Program to use one of these to sample water out of active volcanoes. We work with the EPA, Montana DEQ, other state and federal agencies, as well as, some national and regional engineering and environmental consulting firms. So we can, work from, the small regional environmental engineering firms all the way up to some of the largest companies in the world. use our equipment, use our data, use our techniques for safely collecting environmental data.
What would be the best way for organizations to reach out to you if they would like to work with FIT?
Well, we do have a website. It's www.fairweatherit.com. That has some contact information and some lists of some of our projects. I'm on LinkedIn as well as FIT. If you wanted to meet up with me on LinkedIn, I share some cool pictures and milestones that we've made on there. We do have a YouTube channel, as you alluded to, with some of the different platforms in action. So rather than just hearing me talk about it, you can see the WASP in action behind us, or one of our marine craft driving around. Or if you just want to stick to the standard email, there's info@fairweatherit.com. Will get sent to us, and we can answer your questions and get back in touch with you that way.
Excellent. I certainly plan on taking some of that content and making it available so that people can get the full picture. And last and final question is that usually my favorite type of question to ask people is, what are you working on, anything special or intriguingly fun right now that you would love, that you're allowed to talk about or share?
Oh, absolutely. And they actually both, but the two that I'm going to allude to here might also be a great fit for using these Einstein USD1 radar rangefinders. So one thing that we are working on is doing very, very low altitude multi-rotor flights for geophysical data collection, specifically a ground penetrating radar. So yes, we're going to be using a radar altimeter to help, so we can use a ground penetrating radar flying over the ground. Due to FCC regulations, you can use certain frequencies of GPR, but you have to keep them extremely low, i.e. like a few feet above the ground, to legally operate them in the United States. So what we are hoping to integrate is rangefinders, both downward facing and forward facing, so we can do very slow but very low multi-rotor flights with a GPR payload slung beneath the multi-rotor. So we'd be using the rangefinder pointing down for terrain following. Many of the areas we work at are completely flat. Many of them are not. They're undulating. Or they could have fences or any other thing. So if you're flying your UAV a meter above the ground surface and you have a fence coming up towards you, or a picnic table or whatnot, you want to make sure that you avoid that, that you detect it and avoid it. So we're integrating a downward facing to follow the terrain and a forward facing for obstacle avoidance, so we could go over and then down to avoid any of these obstacles. Our other big project that we're working on is unmanned surface vehicle boat swarms. This would be for that waterfowl hazing preventative method on the Berkeley Pit. So the idea of this is that you would have a number of independent boats, and if you look behind me, that blue boat is our prototype, and we also have some shots of that in our testing. But we would make multiple boats that are outfitted with megaphones, flashing green lights, lasers, other things that the birds do not like, and deploy these on the pit during a period of high alert activity. And the idea of this was, we would have these craft operating in random patterns going around the pit. The birds fly over, they see all this weird commotion going on down there, and they decide it's not a place they want to stop at. They continue flying and go to a safer, more suitable location to rest for the evening. Using that technology as well, we're going to institute a downward facing sonar, so we don't crash into any ground or whatever, but also a forward facing rangefinder, because there sometimes is debris floating in the pit, and we wouldn't want these boats to slam into a telephone pole or a barrel or some other debris that could be floating in there. So I have obstacle avoidance with a forward facing rangefinder on that, so that if one of these objects is detected, the boat can drive around it and miss it and continue operating. So, because if anything happens with these vehicles out on the pit, it's a 100% loss.
Yeah.
So if we hit a telephone pole, it broke off the thrusters, it's a total loss. There's no way to retrieve it. Same with our UAV. If we're flying over something, there's a malfunction, it falls in the water, it's a complete loss. So having these auxiliary sensors integrated into our craft is really, necessary and very helpful for operation and safe use.
Excellent. Ian, I cannot thank you enough. This has been really interesting, and I can't wait to see and hear some of the feedback of people that watch this and contact you because they're like, "Hey, I've got something that I want to do with Ian." So
Yeah.
this has been really, really great, and thank you, of course, for sharing your story about testing out different opportunities such as lidar and finding radar and finding Einstein. So that's deeply appreciated. Thank you for your advocacy, and thank you for your time today.
Oh, my pleasure. Anytime.